Hi, welcome back to Calculus. Today we are looking at section 3.3, some derivative rules. So the good news is we don't have to take limits forever to be able to do derivatives. We have some derivatives that we can say with certainty that we know how they work, and from those we're going to build up to lots and lots and lots of derivatives. So let's get started. We're going to start with really basic ones, and we're going to work our way towards harder and harder ones as we go through this section. So the first derivative that we know is for a constant. So if f of x is equal to a constant c, its derivative then is just 0. And I think that makes sense. Remember, if the derivative is giving us the slope of the tangent line, if you have a constant function, you have a line with a slope of 0. Well, that makes sense then that its derivative is 0. So for example, if f of x is 7, its derivative is just 0. Very, very fun. Powers for any real number n. Now, your book has this one broken down into two parts for just positive integers, and then for any real number n. I just chose to go for the any real number n because I can make it just a little bit shorter. It says that the derivative with respect to x of x to a power. All right, these all work the same way, so this is nice. It's equal to n, the original power, times x to the n minus 1 power. Okay, so the power goes down by 1, and the original power gets multiplied in front. That's it. So I have an example here, and I actually have two more examples for this that I want to do, but I ran out of room, so I'll do those on the next board. So the derivative with respect to x of x cubed, again, the 3 goes in front, it's multiplying, and the power goes down by 1, so it goes down to a 2. We get 3x squared, and that's not too shabby. All right, let's get the next board so I can get you those other examples, and then we'll move on to the other rules for derivatives that we have. Okay, so two more examples using the power rule. X to the 7/8. Let's take its derivative. So again, I take my exponent and I drop it in front. It is now multiplying. And then I have to take my exponent and subtract 1. So I have to do a little bit of work here. 7/8 minus 1 is a negative 1/8. If you need to, convince yourself of that, but it is. Don't change it to a decimal. Leave it as a fraction, please. We don't generally like negative exponents, so I'm going to rewrite this as 7/8 times x to the 1/8 power. Remember, a negative exponent means you could just wrap it down to the bottom of the fraction. So I just wrapped it down and joined it on the bottom with the 8. So we get 7/8 x to the 1/8 power. But one other thing to remember, and this is a perfectly fine answer, but one thing to remember is that a 1/8 power would be the same as an 8th root, right? Those fraction exponents, 1/8 in this case, would be the same as the 8th root of x. And so we can have either of those forms for our derivative. Last example for the power rule for now, the derivative with respect to x of the square root of x cubed. Now, this one's not just, well, it is just a power, but it's kind of hiding a little bit, right? First glance, you're like, hey, I've got a square root. What do I do with that? But really, remember, just like we said back here with the 1/8 power, a square root and a 1/2 exponent are the same thing. Right? A square root and a 1/2 exponent are the same thing. So it's like x cubed raised to the 1/2 power. But when you raise a power to a power, you multiply, so 3 times that half gives me the 3/2. So now I'm taking the derivative with respect to x of x to the 3/2. I bring my power down front, and then I subtract 1. 3/2 minus 1 is a half. So there's my derivative, 3/2 times x to the 1/2, or if you prefer, 3/2 times the square root of x. Either way. All right, so there we go. There's our power rule. Now I've got more to come, so let's move on to the next board. All right, continuing on, constant multiples. So I'm going to introduce a little bit of notation here that is going to be useful for us, and we're going to look at this derivative. If u is a differentiable function of x and c is a constant. Okay, so u here is really just a little piece of substitution that we're using to say this is something that we could take the derivative of. So for example, in this example that I have over here, I want the derivative with respect to x of 7 times x to the 6th. The 7 is the constant multiple that we're going to be looking at, and the x to the 6th is the piece where we know how to take its derivative. Okay, so that's really all this u is doing. It's just serving as a placeholder for something that we know how to take its derivative. And c is a constant. So the derivative with respect to x of c times this function that we know how to take the derivative of is equal to c just times that derivative. So all we have to do, and this is going to be really nice, and we're going to see it in this example, is we can pull that constant out front and just take the derivative of the smaller piece. And that's useful for us because how many times do we see things like 7 times x to the 6th, right? Basically any polynomial has stuff like that running around in it. So we can bring the 7 out front because it's just a constant multiple. Okay. And then the derivative of x to the 6th gives us 6 times x to the 5th. Again, the power comes down front, and the power is reduced by 1. And then we clean it up. 7 times 6 is 42. So our derivative here is 42x to the 5th. So when you get good at this, you can probably just go, hey, 6 times 7 is 42, and then drop the exponent. But in the interest of getting partial credit, if something goes wrong, it wouldn't hurt to write out some of this just so, I can see what you were doing and give you partial credit if you need it. All right, so this is a really handy tool for us because there are a lot of times we have a number times something that we can take the derivative of. All right, let's keep going. Okay, so the next really important tool in us being able to work with derivatives nicely is a rule for sum and differences. So now we have two differentiable functions. Okay, again, u and v here are differentiable functions of x. That just means we're using them as placeholders for something we know how to find the derivative of. So the derivative with respect to x of u plus v is equal to the derivative with respect to x of u plus the derivative with respect to x of v. Basically, you can take your functions in pieces that are separated by either addition or subtraction. Now, you'll notice I also wrote underneath here or minus. So you can replace this and have u minus v and then a minus sign in the middle here, and it all works just as well. And this is really nice because we get big messy looking things like find the derivative with respect to x of this polynomial. 2x cubed plus 6x squared minus 3x plus 1. But the good news is it's not that bad because basically, and you can see I wrote it out in a whole lot of work here, you can split it up across all those sums and differences. So you can take the derivative of 2x cubed and the derivative of 6x squared minus the derivative of 3x plus the derivative of 1. You can do each of those pieces separately, and that's really good. So addition and subtraction are some of our favorites because you just do the individual pieces separately. Multiplication, division, those are not going to be as much fun. But for now, we're doing this. So I brought all the constants out, the 2, the 6, and the 3. And then I took my derivatives. So I have 2, again, times the 3 comes down, and I get x squared, dropping that power by 1. So 2 times 3 gives me 6x squared. There's my first piece. For the second one, the 6 continues down, the 2 drops down in front, which leaves a power of 1 on that x, but anything to the first power is just that thing. So 6 times 2 gives me 12x. And then for the x term, I brought out that minus 3, but keep in mind, now when I drop that exponent is a 1. So it goes in front of the x, but the exponent on the x now, after we take its derivative, 1 minus 1 is 0. So the x basically drops out completely because anything to the 0 power is just 1. And so we're left with just a minus 3 there. Okay, the x is gone. And that's going to happen anytime you have a term that just has x, by the way. Anytime that happens, you're just going to be left with its coefficient. And then finally, the derivative of 1 is just 0 because 1 is a constant. All right. Let's keep going. We have a few more things to look at, and I'm thinking I'm going to make a separate video for the last two. Yeah, that's where I'm going to split this because the product rule and the quotient rule are both kind of messy. So we'll put one more thing on this video, and then we'll make another video for those last bits. All right, so this is my last board for this video. Like I said, watch the next video to get the product and quotient rules. I'm going to make a whole video just for those. All right, the derivative of e to the x. Okay, so this is the natural exponential function. It's really fun, it's really important, and if you take its derivative, you get itself. It is the nicest derivative you're ever going to take, because whenever you take the derivative of e to the x, you just get e to the x. Can't get any nicer than that. Well, I guess the derivative of a constant is 0. That's probably even better. All right, some higher derivatives. This just to close out this section. If y is equal to f of x and y prime is equal to the derivative of f of x, then we have some notation for higher powered or higher order derivatives. Y double prime is equal to f double prime. This is the second derivative. It is the derivative of the derivative. So basically, if you start with an original function, you take its derivative, you get the first derivative. If you take the derivative of that function, you get y double prime, or f double prime of x. If you go past the second derivative, you don't have to do that real often, but if you do go past the second derivative, the notation changes. We stop using the primes because it just gets kind of ridiculous to keep putting more and more of those up there. Now we start using what look like little powers, except we're going to put them in parentheses, and that will denote that they are a derivative. So for instance, if I had a 4 here, this would be the fourth derivative. And it's just defined to be the derivative of the previous derivative. Okay, so you can do this. You can take a derivative of a function and then take the derivative. Just keep taking derivatives. Yeah, loads of fun. All right, so that wraps up this video. Again, make sure you go back and watch the other half where I'm just going to very specifically focus on the the product and quotient rules. So, thank you.